example is microwaves and all these other stuff. But what is different from electric EM waves and mechanical waves is that EM waves do not require a medium. Okay? So that's kind of like a teaser for you. Okay, so let's begin with today's lecture. We have developed an understanding for oscillatory motion. And classical type of oscillatory motion, as we all know, is wave motion. And the idea of waves is that waves are not necessarily static, sitting in one place. Right? As I talk to you, I generate disturbances in the air that is around me, and that disturbance travels towards you. So this is an example of a periodic motion that is moving, that is traveling. So let's talk about mechanical waves. What do we do to create mechanical waves? What are the essential elements? Well, you have to have a source of disturbance, okay? Source of disturbance. And then you have to have a medium. And because these are mechanical waves, you have to have a mechanical medium. What does a mechanical medium mean? Perhaps the best way to describe that is to give examples. For example, when you say a spring, if you have a long slinky spring, right, and you jiggle one end, you notice that the disturbance that you create actually travels. So a spring is an example of a mechanical medium. The air is another example. Any kind of gas, in fact. Liquid, right? If you are on a pond or on your bathtub, if you drop something at one end, you see ripples moving, emanating, and propagating radially. So you disturb the medium. So liquid could be a mechanical medium, solid could be a medium. Right? When you're sleeping at night, and suddenly you hear maybe it's your watch or somebody's watch, the sound waves traveling to the pillow. Okay? A pillow is of course solid. If you are from California, you know very well that earthquakes travel through solid. That's a medium. Solid is a medium. In other words, anything, any form of matter that has elasticity, any form of elasticity, this is very important, that there has to be some kind of elastic property in the medium. That is what makes the disturbance propagate. I guess that's kind of a lead-in into number 3. You have to have elasticity within the medium. Okay. Now, generally, there are two classes of mechanical waves, and these are in the form of transverse and longitudinal waves. And these are all just terms, but they are descriptive terms. What does transverse mean? Every time you pluck the string of a guitar, you notice that it kind of vibrates up and down, and actually it does travel very, very fast. You just don't see it. That's an example of a transverse wave. So here is a cartoon of what a transverse wave looks like. Your medium is the string, okay? And the string, you jiggle one end of the string, and you produce a transverse oscillation, an oscillation that is transverse or perpendicular to the wave propagation direction. So that's where the word transverse means. It comes from. Transverse means perpendicular. So you're jiggling the object up and down, right? But the propagation direction is perpendicular to your jiggling. Right? So this is called transverse. Now you can also have a situation wherein the oscillation is along the propagation direction. What's an example of this? Well, you can picture in your mind a slinky spring, a long slinky spring, and instead of jiggling it up and down, jiggle it along its length. So you will have sections which are compressed and uncompressed. These are called compressions and rarefactions. The expanded part are called rarefactions, and the compressed part are called compressions. And these compressions and rarefactions actually move along the medium. So it's not, the oscillations are not transverse, but it's along the propagation direction. That's why it's called longitudinal wave. And another classical example of this is, of course, when I talk or when I clap. When I clap, what I'm doing is I'm compressing the air that is around my hands. And because of the elasticity of the air, dilute in atoms, it may be, these compressions are traveled towards your ears. Okay? So these are two classes, transverse and longitudinal, and you can generally kind of categorize waves in this form. But again, these are all qualitative stuff. You know, we are scientists, we are engineers. We want to mathematically describe such mechanical wave. So how do we do this? Well, here's the picture. If your wave is traveling, then it must have a picture at time equals 0 and a picture at time t not equal to 0. Let me propose this picture. So consider a profile of a transverse wave. Argument applies for longitudinal, but we'll stick with this because it's easier to understand. So here, draw your attention to the first picture on the left. What you have is a little pulse. On the y-axis is simply y, and the x-axis is x. So think of it as a snapshot picture of this pulse at time equals 0. And so you have a peak, and the peak is displaced from the equilibrium point by something that is called A, and that of course is your amplitude. And the thing, you expect this whole pulse to move eventually to the right. Let us say it's going to propagate to the right. If it does, at some future time t prime greater than 0, it will no longer be at the origin, it will be somewhere here. Now, it will, for simplicity, we will assume that the wave, the shape of the wave is constant. What does this mean? Technically, we say there is no dispersion, that the shape of the wave does not disperse. Okay, we will make the simple assumption. So what does it mean? Well, if you look at the second picture, it is the peak is now no longer centered at the origin, but it is centered at a point along the x that is a distance v times t from the origin, where v is the speed of the wave and t is the time that emanates, the time that passed. So now we say that if looking at the two waves, we say that y of x as a function of y as a function of x and t must be equal to y as a function of x minus vt, comma v prime. That is true because what you're saying is the shape of the wave is the same. Right? So the functional behavior here is the same as the functional behavior here, except that your x prime has now been replaced by x minus vt. Does that make sense? All the same is that the shape looks the same. Okay? And because the subsequent position is no longer x, but x minus vt, then we get this expression. Now notice that the sign of the for a wave that is moving from left to right, the functional dependence is on x minus vt. Okay? What does that mean? It means that whatever is the x here, whatever the x coordinate of any point on this, subtract from that vt and you'll end up with this picture. Right? That's what we're saying. Now if we're moving from right to left, then instead of x minus vt, the parameter here must be x plus vt. Okay? So just